Hey all listeners, this is Pradesh Chaudhary of Quantum Group. This video I'm going to talk about a very good question of electrostatic that will involve a lot of subconcepts like electric field, potential, oscillation under effect of electric field, focusing of electron due to electric field, then capacitance of a charge ring, then charging and discharging all in this one single question. So that is going to be very useful for those preparing for JEE, IIT-JEE Advanced, and obviously for Olympiad aspirant. This is a very long question. This question is from IPHO 2021. Heading of the question is electrostatic lens. So this is going to be a long video. Let me just show you the questions. So this is, you can see in this screen, this is IPHO 2021 electrostatic lens. This question has 5 parts. This is a part A. Part A has a 4 subparts. Part B has 2 subparts. Then part C, the main question, the from which the heading of this question arrives, electrostatics lens. This part C has 3 parts, and then part D, capacitance. This part D has 2 parts, and then finally part E also has 2 parts. So this is a very long question, so the solution will be also be long. For all these questions, there are 2 parts of this question for which I had made a separate video because those things are useful for IIT-JEE. So for those apart, I'll just tell you the link. If you want to see the solution, you can see, and I'll use those results in this question. So this is the IPHO 2021 electrostatic lens. This is a very long video, so let me just give you a quick overview of what we are going to discuss in next 1 hour or so. So let me explain the whole setup of the thing. Suppose this is a ring. Suppose this is a charge ring. The thickness is A, the radius is R. A is very small. This is a charge ring, and we have studied the electric field on the axis. So for very small z, that electric field we have calculated. In this question, we'll also calculate electric field in the plane of the ring at a very small distance from the center, and that will turn out to be, if this charge is positive, this is a positive charge, that electric field is toward the center in the radially inward direction, and if it is a negative charge, that will be away from them. So what is the main soul of this question? This is a kind of a ring, and a beam of electron is in flux here, and the electric field, and this is given a negative charge. So at a very small distance from the axis, the electric field will away direction. So while crossing this, that they will slightly bend, and after that the charge will be, switch off kind of thing, and then they will just converge towards the axis. That is kind of focusing of the charge electron beams. So that's what this question is. So now let's go ahead without wasting time and solve each part one by one. So this is the part A. In this part, this is a ring that I've shown. This ring has a charge Q, radius R, and this thickness of the ring, like this thickness is small a, and the thickness is basically this radius is a, so that is a 2a. This a is very small compared to radius, and then let's see, that is the first setup. The ring is in the xy plane, and the axis of the ring is the along that z axis, and there is a point B in the plane of the ring at a small distance, small r, from the center. So first thing that they have asked, calculate the electrostatic potential phi z along the axis at a distance z from the center. It's a very simple thing. So this is the point A, and here we have to find the electrostatic potential, so phi z. And the simple thing is that this point is at same distance from all the points of the periphery, and that same distance is, this is capital R and that is z, so this distance is square root of r square plus z square. So this, all the points of this ring are at the same distance, the square root of r square plus z square. So potential at A because of this whole ring is simply kq divided by square root of r square plus z square, and this k is obviously square 1 over 4 pi epsilon. That is part 1. And now in the part 2, they have asked us to approximate this electrostatic potential to the lowest non-zero power of z for z is very small compared to capital R. So that's a simple thing. This phi z we calculated, and just use the binomial approximation. Take this r outside this square root, so that will become, this will become, r will come outside, and it will be 1 plus z square by r square power 1 by 2. Take it to the numerator, that will become 1 plus z square by r square power minus half, and then use the binomial expansion approximation, so that will get 1 minus z square by 2 square into kq by r. So that is a potential at A for z very small compared to capital R. And now what they are asking, that an electron is placed at point A at a very small, on the x-axis, z-axis, at a very small distance z from center. So what is the force on the electron? So before that, let's calculate the electric field. So if this charge is say positive, and they are asking that determine the sign of q so that the resulting motion correspond to oscillation. So let's go in the reverse way. If we want the oscillation, so the force should be restoring, so the force on the electron should be towards the center. So if we can have charge such that net force acting here is like this, only then it can oscillate. And for that to happen, we are putting a charge minus q here. So for that to happen, the electric fields should be in this direction, and for this to happen, this charge should be positive. And now we had calculated this potential at a distance z from the center, this kq by r 1 minus z square by 2 square. So electric field here would be a minus del phi by del z. Differentiate this, that we will get kqz by rq. And this is the very simple result that is normally taught in the JEE also, that the electric field on the axis of a ring is kqz divided by r square plus z square power 3 by 2, and then for z very small compared to r, so the denominator become rq, and that's what this is. So we got the electric field on the axis, z axis, and then using this expression we'll find the angular frequency of such harmonic oscillation. Go to the next page. So once again here electric field is along this direction, and if we put it here electron, it will experience a force F in this direction towards center. So this E we had written kqz by rq, and now apply ma is equal to f net. F net is this f, so f net would be minus E into E, and put the value of this electric field here. So A will become get minus EE by m, put the value of electric field, so we'll get A is equal to minus E by m, and in place of capital E, kq by rq, and to z. So this is of the form A is equal to minus something into displacement, so that is the SHM, and this thing whatever in the bracket is the square of the angular frequency. So we have proved that the motion is SHM, and the angular frequency of this SHM is square root of this, that is a square root of kqe by m rq. Put the, if you want to make it in the more explicit way, right, k is equal to 1 over 4 pi epsilon naught. So we'll get the angular frequency of the oscillation, like this is a ring, and if here if I place a electron here, so it will keep on oscillating like this, and that would be the angular frequency. And remember, this is valid only for the small z, very small compared to r. And now this is the part B. So this part B, we have to find the potential in the plane of the ring. So this is the plane of the ring, and this point B is a point in the plane of the ring, and here we have to find potential and we have to find right potential, and obviously the small r is also very small compared to capital R, and we have to find the potential here and have to express this in terms of this q into some constant alpha plus some constant beta into r square. So if we write this, and then we have to find that beta, so that beta will be used in the latter subparts. So let's go ahead here. So this is the plane of the ring. This is the plane of the ring. This is the axis, z axis, and we have to look at then the plane of the ring in the z is equal to 0 plane or the xy plane. So that is a point at a distance small r from the center. This is the radial away direction. Radius of the ring is r, and here the electric field, the expression for the electric field is actually kqr by 2r cube, that is the magnitude. This thing I have derived in a video. I'll not going to give another once again derivation, so I can show you the link of the video. I will share the link in the this is my YouTube channel, and that the video that I'm talking about is latest video. Okay, so this is the video. This electric field near the center and the in the plane of a uniformly charged ring, and I have derived that thing. So using that result, I am directly using that result for this part. So once again, that is a ring, radius r in the plane of the ring. This is a point at a distance small r from the center. R cap is the radial away direction. So at this point, electric field is if this ring is positively charged, so the electric field would be inward. If it is negative charge, that will be outward. So magnitude of the electric field is kq small r by 2r cube. Compare with the electric field on the axis at a distance z, that is kqz by r cube. Here kq small r by 2r cube. So for the same distance on the axis, on the z axis, and in the plane, the electric field is half that amount in the along the axis. So kq small r by 2r cube minus r cap. Once again, if this charge is positive, electric field is in the inward direction. That is what. So electric field will use this electric field, and you can see that derivation there. So for this electric field, if we get this electric field, so want to write the potential here, the increment of the potential, obviously d phi would be minus E dot dr. So this electric field, and dr is obviously in the increasing direction of r, so E dot dr is minus E dr. So that would become simply E dr, the magnitude of E and dr, and that is a k q small r by 2r cube. If we integrate this, so integrate this for small r is equal to 0, the potential here I am writing phi naught, but that phi naught is actually kq by capital R. So I have written just phi, and at r is equal to small r, that potential is phi r. So integrate this, so we'll get here from phi r minus phi naught, and this integration will be kq small r square by 2r 4r cube. So phi naught take this side, so that is this thing, and we had to write this whole expression in this form, q alpha plus beta r square. So take q outside, so this here. So if I take q outside, take q common, so on this part if I take q common, so what will remain with whatever is remain, basically if I want to write in this term, and here whatever will be there, that alpha, we are not interested in alpha because in the latter part beta is asked. So compare this to this, so what will be this beta? So this beta would be simply k by 4r cube, and that was asked. So beta is k by 4r cube, and put value of k 1 over 4 pi epsilon naught, so that is a 1 over 16 pi epsilon naught r cube. So this thing is done. And now they have asked, electron is placed at this point B. What is the force acting on the electron? Looking at the expression of the force, determine the sign q so that the resulting motion would correspond to a harmonic oscillation. So once again, that is a picture. Electric field here is this magnitude k q small r by 2r cube minus r cap. This is with sign. If q is positive, electric field would be inward. If q is negative, electric field would be outward according to this formula. So let me put an electron here, and we want the harmonic oscillation. Once again, if the harmonic oscillation, so it should oscillate, so the net force should be towards the equilibrium position. So for this to oscillate harmonically, the force should be towards the center. For that to happen, this is electron, electric field should be away from the center. For the electric field to be away from the center, that q should be negative. So for the force to be here, the electric field should be like that, and for that thing to happen, q should be negative. So that is thing. And then we have to find the force. Force is simply a charge into electric field. The magnitude of this electric field is this, and multiply the charge of the electron. So force on the electron is in the radial direction, and in this case that would be minus e, the charge of electron, electric field, that is this, minus k eqr by 2r. Force on the electron is this. And now the main part of this question. So let's try to understand this properly. That is the soul of this question, the electrostatic lens. So they're saying we want to develop build a device to focus electron and electrostatic lens. So this is the construction. This ring is, oh no, see, that is the ring, and this is placed like this. This is the ring. Thickness is very small. I have a thicker ring. So this, whatever this ring is, this is the solid thing is the ring. It has a charge q, and there is a, this is the axis, and electrons are moving parallel to axis at a very small distance above the axis, small r. Or they are thrown with a kinetic energy E is equal to mv square by r. So very near to that, this is a ring to some distance here and some distance here. That distance also very small compared to capital R. From here to here, that whole thing is called this active region. So what they are saying, that when the electron reaches the active region, suppose there is a ring and active region starts on this side from here and goes up to here, and see, so what I am showing is out of a scale. So this distance is very small compared to the radius of the ring. So but to explain, I am just showing that. Suppose active region starts from here and extends up to here. So when the electron reaches here in the active region, only then this ring gets charged, and when it goes out of the active region, it becomes chargeless by some mechanism. That's what it is written. So see, so the system is programmed so that ring is charge neutral most of the time, but its charge becomes q when the electrons are closer than a distance d by 2 from the plane of the ring, and that is called the active region. And in the part C, in this part, we have to assume that the charging and discharging takes place simultaneously, and the electric field the space immediately, simultaneously as it gets charged, and we have to neglect the effect of magnetic field. So that is the setup of the question. Now what they have asked. So before what they've asked, let's try to see the electric field in space. So now I have put the ring in this way. This is the ring, and this is the center, this is the axis, and this is a space. I've drawn this space. This is the region R. So this region R here, this is the cylinder. The height of the cylinder is Z, and below also Z. This Z is very small compared to capital R. And this small r, the radius of this cylinder is smaller. This small r is also very small compared to the capital R. In this ring, that is the active region. In this ring, we have to write the electric field. So let me take a general point here. Oh, there is a general point here. So electric field has a two components. This is the EZ component. Actually, we had written electric field Z component that was on the axis, but the small r is so less that it is almost same as it was on the axis. And this ER is the radial component, and that thing also was in the plane. But because this Z is so small that I can also use here in slightly off from the plane. So in this region, at any point we can write the Z component of electric field and the radial component of electric field. And Z component was kqz by r cube, and radial was kq small r by 2r cube. And once again, if the charge is positive, the Z component would be the away from the center, and if charge is positive, the r component would be towards center. That's how it is. So, and in this setup, this thing, so now they've asked that find the focal length of the lens. So what is the focal length? The electron beam would be projected at a distance r from the axis, and because of the radial field, electric field, it will be bent toward the axis and will go through this point of the axis, and this is the focus, and this distance from here is called the focal length. That's what we have to determine. And the sign of Q should be such that the lens is focusing. So let's understand what should be the sign of the charge of the ring so that this can focus, can converge, not diverge. So once again, this is the 2D diagram of the ring. This is the ring, and this is the active region whose width is d. On this side d by 2, on this side d by 2. Here the ring, suppose if I take the ring charge positive, so if the ring charge positive, so Z component would be the away from the center and R component would be towards the center. So if a electron is projected like this, it is here heading towards the active region. So suppose it enters the active region, charge is negative, this ER component will apply a force in the upward direction, and as it goes from here to here, this width of the active region is very small, so from here to here the work done by Ez from here to here and work done of Ez from here to here, that will cancel. So the net effect would be only because of the radial component, and the radial component will apply in the upward direction, so it will go like this. So that is not going to converge. For converge, I need ER in the upward direction, so the force is in the downward direction. So it means that to converge these charges to work as a electrostatic focusing lens, this charge should be negative. So I think that should be clear. So now in the next diagram, so here, now the ring, this charge is negative, Q is with sign. So now ER in the upward direction, EZ is here, and ER we had written K mod Q divided by 2RQ, and with sign that will become minus KQ divided by 2R cube, and there should be one small r also here which I have missed. So that is a KQ small r, and that small r is also here. So now electron beam is here projected with the kinetic energy E, speed is V. So they are thrown with a very fast speed. So what happened that because of this EZ, ER part, the force will have act in the downward direction. So it will start, going in the downward direction this way. But this width is so small, speed is so large that from here to here, that we can say that the bending is negligible. So from here to here, it moves on the almost in the straight path. But as it comes here, so it will have a downward component of the velocity. Effect of Ez, so because of the Ez, this Ez, the electric field force would be in this direction, so it will first reduce the speed in the Z direction, but this part, this component will apply force on the right side, so that will increase. So overall effect as it goes from the beginning of the entering to the active region to the leaving, so net effect of the Z component would be 0. So the overall effect of this ER component would be, it will deflect in the downward direction. So as it just leaves the active region here, because of the force, there will be downward acceleration, AR, radial direction, and that radial acceleration will impart a radial velocity here, and this velocity will intact because the net effect of the Z component of electric field is 0. So when it is leaving the active region, it has also the downward component of velocity. So net velocity direction would be something like this, and because of that, the electron beam will come here, and there is not just one, there will be some electron would be here, so all would be focused here. And we'll see later that this f is not going to dependent on this small r. So if this r is very small and they're very different r, we'll see that all focus at the same spot. So this is a focal length. So you can see here that this f by small r, this is f and this is r. F by small r is cot theta and this is theta, so this is theta, so cot theta can also be written as a v by v small r. This is the radial component of the velocity. So f is equal to r by vr into v. And now here, from here, it will take some time to cross this active region in this direction. Along the z direction, velocity is constant, so the time taken would be d by v to come outside. And the radial direction acceleration, ar would be the radial direction force, e into er divided by m. Put the value of er value is this, so if you put the value of er with sign, because this q has to be negative, so that whole thing is actual positive. So E is here, kq small r by 2 capital R cube, and m was here and minus is here, that is ar. So this ar will give in this time the radial velocity vr. Using first equation, v is equal to u plus at. Initial velocity in the radial direction was 0. So Vr is equal to ART, and this AR and this T, if we put, we'll get this thing. This you can check if I make any mistake. So this Vr, and from here this Vr, we can just simplify R by Vr, we'll get this. Just arrange this, you will get this. And put this small r by Vr, that whole thing. So there is V and there is V, so that V into V will become V square. And that's what we had obtained. Here. If it goes a bit fast, you can pause and just check the expression. So that was f. F is equal to minus 2 small m v square r cube divided by kqed. That's here. And then a few more things, like kinetic energy of the electron is half mv square, k is equal to 1 over 4 pi epsilon naught, beta is equal to 1 over 16 pi epsilon naught r cube, that we had written in the previous. So if I put all those things, and in terms of E and beta, the focal length, we will get this minus E q e d beta. And see, incidentally, this is not depending on the r. It means, once again, suppose this is a ring within a narrow zone. Obviously, it is not depending on r, but obviously that will hold only if the r is very, very small. For the paraxial beam, for all the electron beams which are under paraxial range, the focal length is not depending on the at which height from the z-axis they are being injected into. So that is the focal length. So we have to, and see, this is a positive thing because q is negative in sign. So overall, that is a positive thing. And then now in this case, what had happened, that the electron beam was projected parallel to the z-axis. And now they are saying that in reality, it is not a parallel beam. Some source is located at a certain distance b, and which is more than the focal length from the center of the ring. So consider the electrons are no longer parallel to z-axis, and but they are emitted from a point source at a certain range. So, and then they are focused at a distance small c from the center of the axis. So we have to find c. So that diagram I have not shown, but what they are saying that the situation is something like this. This is the active region, and this is the ring. There's a source of the electron. There's a source of the electron, and that source is at a distance b, and they are projected from a very small angle of incidence, that is written gamma. That will not be used, so I am using that theta. And then from here they are focused somewhere here, something like this, c. So we have to find the c in terms of beta. and obviously some B will also come. So beta that we had obtained in the part A and the question B1 and other known quantity. So let's go ahead. Oh, once again, for the negative Q, this is the active region. The ER would be in the upward, EZ would be towards the center like this, and this is the source here at a distance B. Electrons are projected at a very small angle theta from the axis. The velocity is V. So they reach at this point on the active region here on this path. So here the component, let me make the component of the velocity. So the component along the axis would be the V cos theta perpendicular to axis V sin theta. Theta is very small and measured in radian. So cos theta will be tending to approximately 1 and sin theta would be tending to theta like this. And this theta, and this is r, so theta would be approximately also tan theta. So theta would be small r by b. So v theta mean vr by b. So that is the this component like this. And now the same very narrow active region, Ez effect in from here to here would be neutralized, so there will not be any change in the z component of velocity on leaving the active region. Initial velocity in the radial direction, the upward, and the electric field is upward, electron is there, so there will be downward acceleration. So the acceleration should be large enough so that finally it can revert the direction of velocity. So after leaving the active region, and this is the acceleration after leaving the active region, the velocities are like this. 1 minute, like this. This is the velocity. Z component does not change because of the effect of this. Initial velocity was vr by b and the final velocity in the radial direction this, and it goes along net velocity in this path and is being focused at this, and this is c. In the same way, ar is equal to e ar by m, and we had written earlier also the same here, the radial component of the electric field. Same way, time to cross this active region is d by v. Time to cross is d by v, and in this time this acceleration will make a change in velocity. So again apply v is equal to u plus at. This direction is positive, so this velocity would be negative. So vr is equal to, that is u is minus vr by b plus ar into t, and we'll put the value of ar and t here, and we'll put letter and see here. This c by r is actually this v by vr. C by r is v by vr, or we can write this theta, take theta, this cot theta is c by r, and from here cot theta is v by vr. So that is the thing, c by. So and so this c is equal to v into r. See, this is looking to be vr, that is also, this is the radial component of the velocity, and this is the overall x component of z component of velocity and r. So v into r divided by vr. So once again all those things is written here. Time was this, ar is this, vr is this, and c is this. So put all those things. So v into r, that is vr, this vr radial, so that whole thing we are writing here. So minus vr plus art. In the ar also minus sign is here, so all the minus sign is taken outside, and this thing is the whole, this ar, and this t is equal to d by v. So all that, divide the numerator denominator by vr. So if you divide this, that is 1, and that is 1 by v, and dividing by vr, so that r will be cancelled in the denominator, this v, so one more v will there, that is v square. So that we've got, so we've got this c. That was us, and basically we want to write in terms of beta. So beta we had written, and the connection of beta and k was 1 over 4 pi epsilon naught, and beta was 1 over 16 pi epsilon naught m r cube, something like that. If we put that, you will get this c. So we've got c. In terms of the kinetic energy also, this mv square is there, half mv square is equal to E. So just write in terms of all those known quantities, we'll get this thing. So now is the equation of this the equation of a thin lens? So now is the equation of a thin lens 1 by b plus 1 by c is equal to 1 by fulfilled by this electrostatic lens? Is it really a kind of a optical lens? So just we have to show it by explicitly calculating 1 by b plus 1 by c. 1 f we had already calculated. So see, c we just calculated this. The thing is that the whole setup is like this. That was a electrostatic lens. This was a source at a distance b here, and this is a c. If it is actually a kind of a optical lens, that is an object, that is image, so using Newton's formula, 1 by x plus 1 by y should be 1 by f. If that follows, that is fine. So let me check, and let me arrange this. Just take a reciprocal of that thing. F was also given. F was not given, we had calculated f, so that was f, and if I take the reciprocal of this, that would be 1 by c, would be basically I will take minus here, so then I'll take reciprocal. Minus 1 by c would be 1 by b plus qe d beta by e. Take 1 by b on that side, so that will become 1 by b plus 1 by c is equal to minus qe d beta by e, and you can see that is the this thing is the nothing but see this and this, so this is nothing but 1 by f. So we have obtained 1 by b plus 1 by c is equal to 1 by f, satisfying the lens formula. So this is fulfilling, this equation of the optical lens is fulfilled by for the electrostatic lens. So it is indeed the focal length of this optical lens. So part C is done. Now this part D, actually this is the toughest part, the second toughest part. Capacitance C of the ring. Consider ring has a finite width 2a. Remember, a is much smaller than r. That is also a very long thing. My last video for this thing only about 1 month back. So let me show the. So it is that, see, capacitance of a metal ring, and here that I derive, and that capacitance of this ring is C is equal to 4 pi square epsilon naught r ln 8r by a. You just, it is a 22-minute video, quite detailed. I've explained all those things. So that thing, for that thing you can go through that video. Basically in the latter part we have to use this capacitance, and we don't have to write the whole expression of the capacitance in the latter part, just write only C there. So we'll use that thing here. Okay, so I calculated the capacitance C, and with in terms of C we'll use the latter thing. So that part I'm not going to do in this video. So now see, this is very important thing, that what was happening, that this was a ring. We assume that when the electrons reach in the active region, this gets charged and it remains the neutral at all other times. It's not realistic. So to get it charged, this is a metal ring, so it has a capacitance. So we connect it to the battery. Charging and discharging will allow, like when it will reach to the active region, will start charging, and when it will leave the active region, will just disconnect the battery, so that will discharge. So that is something. This is a ring, and this ring has a capacitance C. There is a resistor, this is the ground, this is a battery, and this is a movable switch. So when the switch is connected to here, it means this ring is getting charged because it is connected to battery. Then I can flip this switch to this point. So now that is connected to ground through the resistor, so the all the charge that is come through the charging process, that will go to the ground through this resistor, that is discharging. So that is done. So now see what they've written. When electrons reach the active region, the ring is connected to source of the voltage. When electrons pass the active region, the ring is connected to the ground. So that now we are mechanically charging and discharging. When it will come to the active region, we'll just connect to the battery, and it will pass the active region, will connect to the ground. So that will be discharged. So the resistance of the contacts is R naught, and the resistance of the ring can be neglected, or if you don't want to neglect, just include into the other contacts. So overall the net resistance is R naught. So now we have to find the dependence of the charge on the ring as a function of time, and make the schematic plot of this dependence. Q is equal to 0 corresponds to time moment when the electrons are in the plane of the ring. What is the charge on the ring Q naught when the absolute value? What is the charge on the ring, that is Q naught, when the absolute value is maximal? Capacitance is C. You don't have to use the actual expression, just write every expression in terms of C. The polarity is for the indicative purpose. The sign should be chosen so that the lens is focusing. See, we've seen that for the lens to focus, the charge should be negative. For charge to be negative, so if this is zero potential, so their potential is positive, so that will, the charge of this ring will be positive. So this polarity should be opposite. I mean, this bigger terminal should be here. I mean, that should be like this. It should be actually like this. That's what they are written. The drawn polarity is only for the indicative purpose only. So actually for this ring to act as a focusing lens, so its charge should be negative, and for the charge should be negative, sir, so negative terminal should be connected. It should be like that. So that will be using that, like that. Yeah. So here now we have to find the charge on the ring as a function of time. So see, that whole thing that was written. See now here, this is the ring here. This is the active region here. For the negative charge, the ER is in the upward, EZ is like that, and the electron will come like that, and when it will reach to the active region, just when the electric field would be V, velocity would be V, and this EZ will not change the Z component of the velocity, so it will go with the V. But because of this ER, there will be some downward component that will show. So, but what they have said, electron is going like that, and obviously from here to it will deflect. But the moment of time t is equal to 0 would be taken when it is exactly at the ring mean at here, that is t is equal to 0. From here to here, the total time would be d by v. So from here to here, d by 2v. So this is the entry point, this is the exit point. This time is t is equal to 0. So this here. So when the electron would enter the active region, the time moment would be minus t by 2v. And when it will leave the active region, the time would be d by 2v. And this is for during charging. And now the charge is not constant. This is a variable negative charge. So this setup would be like that. Here during charging, this was a capacitor like ring, it's capacitance C. This is a ground, potential is 0, and we shown that told that this polarity should be like that. So the battery voltage is V naught, so potential of this point is minus V naught. This is the resistor R and this V. So at time t, suppose this ring has got some charge Q, obviously that will be negative. Here it is with sign. So now this is higher potential, this lower potential, current should flow like that. So a current I is flowing like that, and this Q would be obviously CV. I would be the potential difference divided by our potential difference is V plus V naught, V minus V naught. So that I, and I is also because charge is coming from here, so this charge will decrease. So I is equal to minus dq by dt, and also I is equal to V plus V naught by R. So put all those equations, make a differential equation and solve them. Go to the next page. All those things, Q is equal to CV, I is equal to minus dq by dt, I is equal to V plus V naught by R. Simplify that. So here minus dq by dt, V is equal to Q by C, and then R, take LCM RC, that you will get this. So this is the first order differential equation, and just solve it with suitable limit. So dq divided by Q plus CV naught minus dt by RC. So the charging starts at minus d by 2v, and the zero, initial charge was 0. Within the charging time, at time t, the charge has become q. So we integrate it, and this integration will become ln q plus q naught by cv naught, and all those things. If you just put it that, and I'm just directly writing that. So basically we'll get this charge during charging time is equal to minus cv naught 1. That part is increasing. This minus sign mean the magnitude is, charge sign is negative and the magnitude is increasing. Charging will go on till plus d by 2v. So the charging increasing, the magnitude of charge is increasing. So this charge q is maximum at t is equal to d by 2v. So in the next page, this what we got. This q is, the mod q is maximum at d by 2v. So if I put it that the q naught is the mod q max, that will be here taken mod, that cv naught, place of d just put d by 2v, so that will overall become d by v, and this d by v by rc, that is the maximum charge. Then after that, when it will leave, so battery will be disconnected and that resistor will be connected to ground, that will be discharging. So from the, for the discharging part, let me say that this t naught is d by 2v when it leaves the active region. That time is t naught. For t greater than t naught, the circuit would be like that. Capacitor, ring as a capacitor, resistor are directly connected to ground. That is normal discharging. If I count my time moment from here, so charge would be whatever charge that is often say q naught. It will be simply q naught e power minus t by tau or t by rc. So I will take a transformation of time. So using transformation of time, that the initial charge was minus q naught, that is a minus of t minus t naught by rc, because the discharging starts from t naught. So that is the basically this time interval after discharging starts. So directly I have written, that is a very direct result. So use all those things, whatever is written, just simplify that thing. So this was before charge reaching active region, the battery was not connected, battery was connected here, so charge was 0. This thing is during charging, this is a charge during charging, and this is a, this whole thing, see this t naught, you put t naught and q naught, that maximum charge, put all those things, we will get this. And check this also, because see already this is a long video, so purpose of the video is to make the concept clear, what is actually happening. Well, solve all those things, I might make an error, because error is a natural thing. Also it will take a lot of time, so this calculation I have already written. So I think things are making sense. So now let's go ahead. And this plot, this is a charging, this is increasing, but charging continues till d by 2v, and after that this is a discharging. The time constant of this discharging would be is rc. So here let's try to understand. In one time constant, 63 discharging is complete. What do you mean? In one time constant, 37% of the initial charge is remaining. But this, the question, I'll show the question, but let me explain this diagram. In this, suppose this is RC is very small. This RC is very small. This time constant is very small. So it is discharging very fast. And this diagram is not up to the scale. So in one time constant, maybe in some millisecond kind of thing, the charge is the 37% remaining in 1 by e times. In 2 time constant, that will be 1 by e square. So it will, after few time constant, it will be practically uncharged. So total, basically just after leaving discharging occurs, but the charge will come to 0 very soon. Theoretically it will take infinite time, but practically very soon it will become discharged, because time constant is given very small. So for the sake of simplicity, we can say that during whole discharging time, the electron is moving parallel to the parallel to the zx. Why I am saying that? That I'm just saying for the whole discharging time, but that whole thing is very small. And after few time constant, the charges practically become zero, and when the charges practically become zero, so then effect of the all the VR and is no longer there. So now see, now once again focusing this case, now they will. Now in this part, that is the focal length of a more realistic lens with non-instantaneous charging. So this part of the problem we will consider action of a more realistic lens will again neglect the width of the ring to a assume that electrons travel parallel to z-axis before reaching the active region. However, charging is no longer instantaneous. Focal length of the length we have to find the same way. F by V is R naught C. That R naught C is time constant. This F by V. So what is F by V? Suppose if the after crossing the active region, it has to travel a distance F, and the V is the velocity along that time. So this F by V is the time taken to reach the focal point after crossing the active region, and that time is much longer than that time constant. The time constant is so small. So we have to find basically after coming from the active region how much the radial velocity has come. From their deflection we'll write. So for calculation of the whole VR, we'll find the AR would we will write dVR by dt, and then integrate AR from with respect to time. For that integration, in the integral I'll set the time from 0 to infinity, but once again that is 0 to infinity, but practical effect is only for very small time. So that is the approximation that we are going to take. So once again here, that is the whole setup like this. This is for the negative charge. This is during discharging. This is a variable negative charge. Electric field radial component is above. Electron beam is entering like this, and because of that this width is so small, so that it is going like that, and from after exiting the active region it has got a velocity here in the radial direction that I have not shown here. That AR same way is ER by M, and ER is K Q small r by 2r cube, and E by M is there. So this is actually positive because Q is negative. So let me write that whole things to be say some gamma, this K E by 2m r cube gamma, and that is small r. So gamma is that thing. Now go to next page. That electron is going like that with energy E, velocity V enters here because of the electric field. It has acceleration in the downward direction, so because of that thing it has got a radial velocity, and this velocity almost unchanged. And then finally is focus here, the focal length is F. So that F is equal to C, F by small r is equal to V by VR. So F is equal to RV by VR as we had written before. So main thing is to calculate that VR. See, AR is equal to dVR by dt. AR I had written in the previous page. So dVR is AR dt. AR is that, so minus gamma RQ dt. So we have to integrate that thing. So go to next page. Before integrating, I am writing that whole QT that we had obtained. dVR is this. Now integrate that thing. So if I integrate that thing, so you see the limit of integration I have taken from minus d by 2v to infinity. But for that limit is divided into two parts. One part is for the charging, that is minus d by 2v2 plus d by 2v, and for the discharging q by 2v to infinity. And once again the real effect of this is very small time after that. So though it is infinity, so the actual effect would be very small. So during that effect the R is not appreciably changing, so we can treat R as a constant during that whole process. So this gamma R is taken to be outside, and this Q charging is this is a charge during charging, and this Q discharging this. Carefully put all those things and very carefully integrate all those things. Integration is simple integration, but lot of terms are there, so error might come. So integrate carefully. So we will finally obtain this. VR is equal to 2 E beta V naught dr by mv, and F is equal to focal length is RV by VR. So put that thing, and in terms of the parameter that we had written, beta E kinetic energy half mv square, beta initial in the part A. So this is the focal length that we will obtain. F is equal to E. That is the final. So focal length in this case of a more realistic lens we have obtained. Oh, just simplify that. I think that is the same thing. Okay. EC naught, EDB, same thing. So we obtained this. Now the last part of this paper, this question. The result is similar. You see that the result F is similar to that operant part C, whereby the Q is substituted by Q effective. Find the expression of the Q effective in terms of the quantities given the formulation of the problem. So in part C, we had obtained this F. This is positive, actually this Q is negative. And we have to replace that Q by Q effective so that we can compare this focal length in the part C to the focal length in the part E. In part E, we have obtained this thing. So if I compare, this is E, this is E, EDB, EDB. So in place of Q effective, that is CV naught, minus CV naught. So minus is obvious because the charge is negative for focusing. So basically that whole thing we can replace to, I mean, the lot of the calculation that we have done here in this part, like calculation of the Q, variable Q, that whole variable Q can be replaced by simple Q, that is a CV naught. If I replace that whole variable Q, and if I want to avoid the integration, so in place of that I can just put a constant Q, that is a minus CV naught, and that then the focal length would be same as that is obtained in the part C. So that's all for this video, this long video. This is a really very good question to understand the whole dynamics here, the focusing, the oscillation, the capacitance, the charging, discharging. Indeed, that is a very beautiful question. I really personally like this question very much. I hope you all like that. But before just watching this video, if you haven't attempted, so you will really not like. So I request you to just give this question an attempt. It is indeed a gem of the lot. Thank you.